Hi, I'm Eli Winterscheidt, and this is Lab 1 Constant Velocity. This lab focuses on the movement of an object that has constant velocity, so one that has a net force of 0 or is in equilibrium. In this case, as you can see in the tracker window, it's a basketball being rolled along the ground. The experiment consists of analyzing the data in Tracker and then comparing it to a model made in Python. So the way we do this is using a few different formulas. So the formulas that are used are the momentum principle, the velocity update formula, and the position update formula. And these two are only used to actually find the position update formula. Because we have a constant velocity, these two won't actually come into effect. And the position update formula is the one we use, and that states that the final position is equal to the initial position plus the average velocity times delta t. So if you direct your attention to the tracker window in the bottom left, you can see the video playing along of the basketball moving in the positive x direction and this was filmed at 240 frames per second just for clarity, so it moves quite slow. And right there you can see, just a little note, that the point mass moves from the x-axis down to the bottom of the ball, and this is okay just because the y-axis doesn't really matter in this data that we're doing. So as long as it's at the same x direction, which it is, it was just a bit easier to find that x position at the end on the bottom of the ball. It'll be fine. So yeah, the diameter of the ball is 0.239. That's what I used to calibrate the video. And so the initial velocity that I found was 1.517 meters per second, and the time between start and finish was 0.636. Now if you look up to the top left corner, you can see the glow script, and there's the ball mass, which doesn't actually matter in this case, since we have a constant velocity. This is the ball position, which started the vector 0, 0, 0. And the ball velocity, the initial velocity, which I found in Tractor, 1.517. And delta t, I set that to be the same as the time between frames. Since we're at 240 frames per second, it's 0.00417. And this is the while loop, which runs the whole script from t0 to the end. So fnet, this is really important. Fnet is 0, 0, 0. This is what says that we have constant velocity. So, and because that's all 0, a velocity update formula won't actually do anything because it's just adding itself to 0. And then the ball position, or the position update formula, is what's driving the whole thing. So when we run it, we can see that the ball moves in the positive x direction just like in Tracker, and we have a nice straight PT line that looks very similar to the one in Tracker. But when we plot them together, we can see that they're not quite the same. Specifically, the model line is quite a bit higher than the experimental line. So this is because we don't account for friction when we say that it's constant velocity. So in our glow script, it's not going to actually predict what's happening in here. And so we can see it's slightly concave, and that's because we have a bit of friction going on. Now, if we wanted to create a more accurate model, we would have to have that fnet variable set to have a negative x component. And so the way that we would do this, we would find the force of friction, which is force of friction equals the coefficient, in this case rolling friction, times the normal force, which again in this case is the opposite of gravity, so 9.8. And so I found the coefficient of rolling friction on an online reference table, and a similar one. So it was hard rubber on medium compacted soil, and it was 0.06. So I used that to find friction, and the force was negative 0.36. Now I put that into glow script, as you can see right here. And so when I run it, you can't actually see, but this imperceptibly slows down. But right here you can just barely see it's very slightly concave. So now when I click here, you can see when they're plotted on top of each other, they're very, very similar. The only things out are some jagged curves, just because the point masses weren't plotted exactly in the center. Now, what can be concluded from this is that, well, that there is no constant velocity in real life. It only exists in ideal physics. And this is because we have friction and air resistance, and so any object moving will eventually slow down no matter where it is. Even if it's in space, that's not a perfect vacuum, it'll slow down eventually. Yeah, so thanks for watching.